Welcome to the Explainer. Today, we are diving into a massive shortcut in the world of AI. It's a technique that lets us build unbelievably powerful models way faster and with a lot less data than you'd think was possible. We are talking about transfer learning.
But first, I want you to think about something. Think about any skill you've ever learned, maybe riding a bike or learning an instrument. Now, what if every single time you tried something new, you had to start from absolute zero? Like with zero knowledge of how anything in the world works.
It would be pretty much impossible, right? And that's really the core idea here. On one side, you've got learning from scratch. That's the hard way. It takes a ton of data, a ton of time and energy, and you're literally starting with a blank slate. But the other path, the smart path, is learning from an expert. You get to build on what they already know to tackle a new, related challenge. It's faster, it's way more efficient, and honestly, the results are just better.
Well, you'll be happy to know that in the world of artificial intelligence, this exact shortcut isn't just some nice idea. It's a real, powerful, and established technique, and it's called transfer learning.
Okay, so let's get right into this shortcut and meet the so-called experts that make this whole thing possible.
So what exactly is it? Well, officially, transfer learning is a technique where a model that's already been trained for one big task, like, say, identifying thousands of different objects, is then reused as the starting point for a brand new but related task. The point is, we're not reinventing the wheel here. It's more like we're taking a high-performance engine that already exists and just putting it into a new car.
And you know, these expert models have an amazing history. It all started with pioneers like Lenet 5, way back in 1998, which had around 60,000 parameters to recognize handwritten numbers. Then, bam! 2012, AlexNet comes along and just blows that away with 62 million parameters. And then, just 2 years after that, VGG16 pushes it to a mind-boggling 138 million. The sheer amount of knowledge these models have has just exploded.
But that brings up a really interesting question, right? How do these digital experts actually learn to see the world, especially when we're talking about images?
So for an AI model, like a convolutional neural network, or CNN, it's kind of like how a person learns to draw. In its first layers, the model learns the absolute basics, simple things like edges, corners, and blobs of color. Then, in the middle layers, it starts putting those together into more complex things like textures and basic shapes. And finally, in the deepest layers, it assembles all of those pieces into complex stuff we'd instantly recognize, like an eye, or a wheel on a car, or even an entire face.
All right, theory's great and all, but let's see this thing in action. Let's say we have a really important job. We're going to build an AI that can spot emergencies just by looking at images.
But here's the catch. Here's our big challenge. We only have a small, custom set of photos of emergencies and non-emergencies. If we tried to train a massive model from scratch on just this little bit of data, well, it would be a total disaster. It would be incredibly slow, and it would probably just end up memorizing our few images instead of actually learning anything useful.
So, this is where we need to bring in an expert. We need a pre-trained model. The question is, which one is the right fit for this specific job?
Let's think about this. We could use a model called VGG16 that was trained on MINST, which is a dataset of black and white handwritten numbers. But our emergency photos aren't simple digits, right? They're complex, colorful, real-world scenes. So that's not a good fit. A much, much better choice is a VGG16 model that was trained on ImageNet, which is this enormous dataset with 1,000 different categories of real-world images. We're talking everything from cats and dogs to cars and boats. Now that expertise is a perfect match.
So our strategy becomes crystal clear. We're going to take all of that incredible general-purpose knowledge that VGG16 has about the visual world, and we're just going to gently fine-tune it to focus on our very specific task, telling the difference between an emergency and a non-emergency.
So what does fine-tuning actually mean? It's really about adapting that expert model. What we do is we freeze the early layers. Those are the ones that learn to see all the universal stuff like edges and shapes. That knowledge is way too valuable to throw away. Then we only retrain the last few layers on our small specific dataset. It's kind of like teaching a seasoned doctor a new specialized surgical technique. You don't make him go through all of med school again.
So, after all that, what was the result? The payoff for our strategy? We achieved a 95.4% accuracy on our test images.
And that is an absolutely fantastic score, especially considering we did it with a tiny fraction of the data and computing power we would have needed to start from scratch.
It really all boils down to this. By standing on the shoulders of giants, we got these incredible results with way less data and way less effort. And that is the power of transfer learning.
That whole fine-tuning process is so cool. But how does an AI model actually learn during that phase? How does it improve? Let's take a quick peek under the hood at the engine that drives it all.
Okay, it's all driven by something called an optimizer, which is really just trying to find the point where the model makes the fewest mistakes. The easiest way to think about it is like a hiker trying to get to the very bottom of a valley. One way to do it is to take lots of small, quick, but kind of noisy steps. You might zigzag down the hill a bit. A better method is to look at a small patch of ground before each step, which leads to a much smoother, more confident, and direct path downhill. That's really all that's happening. The AI is just finding the most efficient way down the hill to get to the best possible answer.
Okay, let's zoom out and bring this all home. What's the big payoff here? Why is this technique so fundamental? Why is this such a game changer in the world of AI?
Well, the advantages are huge. First, it drastically, and I mean drastically, cuts down on training time. It also requires so much less data, which is usually the biggest hurdle. On top of that, it almost always gets you better performance. But maybe the most important thing is that it democratizes AI. It allows so many more people, more companies, and smaller teams to build incredible things on top of cutting-edge research without needing their own supercomputer.
And all this really leaves us with a pretty powerful thought. If AI can inherit knowledge, if it can stand on the shoulders of its digital predecessors just like we do, what incredible things will it learn to do next?